The next speaker is Tony Jebara. I've known Tony for, I guess, quite a while. We were both grad students together in Boston, and then Tony's been at Columbia since then. He's done really nice work in machine learning, also in graphics, also in computer vision, and does some really nice work with graphs and some combinatorics and algebraic structure. And having Tony here, I thought I'd wear one of the t-shirts I had from back in grad school, and it doesn't fit as well, but.
Okay, thanks Cheyenne, and thanks to the organizers for inviting me, and thanks to Alan Key for letting me switch slots with him. So I'll be talking about something that's a little different from the structured sparsity and the sparsity method. I'll be going towards the realm of combinatorics today and talking about graphical modeling, which is an important problem in machine learning, and the use of combinatorial techniques such as perfect graphs, and this is joint work with my student Adrian Weller. And so just as a quick reminder, graphical models are used a lot in various learning and inference problems. And we basically depict a graphical model as a bipartite graph. We call that a factor graph. And this graph connects variable nodes to these factor nodes called vertices. And the x nodes are just discrete random variables. The phi's are positive functions. And basically what we're saying is, this probability distribution over n variables breaks up into a small product of small functions. And we describe how that thing breaks up through this kind of graphical model. And this is showing a more efficient way of representing a big probability distribution and storing it also more efficiently. And so for this particular example, we can see this distribution over 6 variables breaks up into a product of these little functions, phi's, that are over pairs of variables or triplets of variables. And so it's much more efficient to store these types of probability distributions when we use graphical models. Now, what do we like to do with graphical models? In addition, the main computational things we like to do are to do either marginal inference or maximum a posteriori inference. And so in marginal inference, what I'd like is to compute from the big probability distribution, the little marginal distribution over one of the variables that I'm interested in. Okay, so that involves summing over all the other variables, so that's typically a lot of work. Or I'd like to do map inference, which is find out what's the highest scoring configuration of these random variables, the one that beats all the other ones. And in general, both of these types of things are NP-hard. So Cooper proved in 1990 that marginal inference is NP-hard, and Shimoni showed that map inference is NP-hard. And in fact, things are even worse. They're both hard to approximate. So even if you want to get answers that are not so bad, things are also hard. But there are some types of models where things are easy. And the main one is on acyclic graphical models. So things like tree structures. And so Judea Pearl showed methods for efficiently inferring both map and marginal inference. And the basic idea is to run this technique called belief propagation or some variation of it. And this does great for tree structured models when you want to do inference in trees. And so you can, for any acyclic model, you run this technique called belief propagation. If you want to do marginal inference, you run the sum product algorithm. You basically send messages from a variable v to a factor u. So from a circle to a square, you send a message, which is a product of all these other messages. And then you send messages from the factor u to the variable v, which is a sum of a bunch of products as well. And you iterate, and this efficiently converges and recovers the marginals we want, as shown by that solution over there. And that gives you marginal inference. That's what's called a sum product algorithm. You're basically doing a bunch of summations and products. If you want to do map inference or maximum a posteriori, just replace the summation operations with max operations, and you'll also be able to solve the map problem. So this is great, and it's been proven to work on trees, and we've known this for a couple of decades now. But it turns out it also seems to magically work okay, not perfectly, on loopy models. And so if you take, for example, this model, it's not a tree-structured graphical model. This is an alarm network, which is used to diagnose if people are having a heart attack in the emergency room. And you can see that running the algorithm gives you marginals that are almost as good as the best marginals. So there's a little bit of error in it, but it kind of works. So you just keep running this algorithm, even though it's not on a tree, you iterate it, and you kind of get good answers. You can run on this algorithm, which also has a lot of cycles and is not a tree. You'll also get a pretty good answer out of the sum product algorithm. that's close to the true marginals. You can also run this medical diagnostics network called the QMRDT network, where you've got diseases and symptoms, and infer the marginals of diseases, again, pretty accurately compared to the exact answers, which are very hard to obtain. And here's another example with the max product algorithm. This is a loopy model as well, not a tree, and this is solving a bipartite matching problem. And here, actually, the max product algorithm gives you the exact maximum a posteriori solution. Again, it's not a tree. And it turns out you can prove, so we proved that for bipartite matching problems, the max product loopy algorithm will actually give you the optimal answer in cubic time, in n cubed time. And so it turns out there you can actually make a nice formal proof, and it's not a tree, but what you do is you unwrap the messages as you go around the cycles, and you form this kind of infinite tree of unwrapped messages. And you can show that the tree, you only need a depth of omega n, and that's enough to guarantee the runtime of the algorithm. And so it turns out that loopy graphical models can actually admit efficient inference. You can use either this algorithm or some other algorithm and still get something correct in polynomial time. So the goal of this talk is to say, well, what is the class of such loopy models beyond trees where we can get exact inference? And it turns out we'll be able to prove certain things by using perfect graph theory, and you can characterize what's the set of efficiently inferable loopy models. Okay, so what is a perfect graph? Perfect graphs were invented by Claude Berge in 1960, and there's a whole community of combinatorics researchers that work only on perfect graph types of things, literally hundreds of researchers. And the definition of a perfect graph is a graph is perfect if all its induced subgraphs, so all the subgraphs of that graph, have coloring number equal to clique number. And also, Berge introduced the strong perfect graph conjecture, which is a big problem that's been open in that combinatorics community for 50 years. And what's interesting for us, if we're interested in computation, is many NP-hard problems were shown to be solvable in polynomial time for perfect graphs. So this is a result by Grotschel, Lovash, and Shriver. So for example, coloring a graph is hard, but coloring a perfect graph is easy. Finding a big clique is also easy in a perfect graph. Finding a stable set is also easy in a perfect graph. These are otherwise NP-hard problems. So here's a quick description. Coloring, again, I give you a graph. You have to color the nodes. You have to use as few colors as possible, and no adjacent nodes can have the same color. Max clique, basically find the biggest clique of all pairwise adjacent nodes. And then the stable set problem is find the largest set of nodes, none of which are pairwise adjacent. So that's the last problem. So those are always hard in general, but on perfect graphs, they're easy. And on weighted perfect graphs, you can solve weighted variants of them. So for example, I can have weights on all the nodes, and I can say find, so here's a stable set on the left. I can say find me a stable set with maximum weight. So pick the set of nodes so that no two are adjacent pairwise, and maximize weight. And you can get a score of 8 if you pick node 8 by itself. And a maximum weight stable set is pick the most nodes with a maximum score. So then you'd actually include the 0 weight node as well. Okay, that's the maximum weight stable set. And so these types of problems are solvable and efficiently. So for example, we can solve maximum weight stable set by a linear program. And what we do is we write this weighted linear program over here with the weights inside the F vector. And we form this matrix A, which is the cliques vertices incidence matrix. So for this graph, which is actually perfect, we can form this matrix. It's a list of all the cliques and the nodes inside the clique. And then this constrained linear program turns out to solve for a binary solution, even though it's in general, it doesn't have to be, but if your graph is perfect, the linear program is binary. And so unlike, let's say, compressed sensing where we guarantee sparsity, perfect graphs can guarantee that our linear programs are going to be binary. And we can solve these in cubic time in n, or times the square root of the constraints. You can get rid of that square root of m by solving for the maximum weight stable set through a semi-definite program, and that's what the semi-definite program looks like. You're solving for here a matrix M, which tells you where the maximum weight stable set is. and you have some constraints on the M given by the perfect graph, and you have some weights inside here, and you solve for this thing called the Lovász theta function, and that also finds the maximum weight stable set. So we can solve either a semi-definite program or a linear program to recover the maximum weight stable set, and that's otherwise a hard problem. Okay, so there's many other perfect graph theorems. Turns out a big result was the strong perfect graph theorem was proven after almost 50 years by Chudnovsky et al. And they basically showed that if a graph is perfect, that means it has no odd hole and no odd antihole. Okay, so a hole is basically a subgraph, which is a chordal cycle of length at least 4, and an odd hole is just an odd length, and an antihole is a complement of a hole. So on the left, you see a perfect graph because there's no hole. In the middle, you've got a 5 hole, that's odd. On the right, you have a even hole, that's even, so that's still perfect. There's other nice theorems, ways of kind of growing perfect graphs. If I have a perfect graph on the left, I can bring a new node x7 and connect to it. As long as I connect to x4 and all its neighbors, then the graph on the right is also perfect. So this is called the replication lemma. I can grow perfect graphs by bringing one node in at a time and kind of replicating that way. I can also take 2 perfect graphs and I can paste them on a clique, and then the resulting graph's also perfect. That's another kind of nice construction as well. So what our goal is going to be is to reduce map estimation to the maximum weight stable set on a weighted graph. And if this reduction nicely produces a perfect graph, then we say actually now map is efficient. And so this will let us prove the efficiency of map for, first of all, acyclic models, which has been known for a while. We can reprove the bipartite matching model results. We can prove associative models are also going to be efficient for map. We can also show that as long as models are not frustrated, we can solve the map problem. And we can also show that if they're slightly frustrated, we can solve the map problem. I'll show what I mean. And we can also do marginal inference, but I've kept that in yellow because I won't have time to go into that today. We can also use these techniques as well for marginal inference, but not for today. So remember map inference, we're trying to find the maximum scoring x, and here I've written the potential functions as log potential, so this is the map estimation problem. We've got n variables, and we've got a potential function for each setting that gives us a real number, and we're just trying to maximize x in this probability or the log probability over here. And we'll assume here that n is finite, all these potential functions are finite, and all the random variables are discrete random variables in a finite set. So here's how we convert a graphical model into a hopefully perfect graph. And what we call this graph, it's no longer a graphical model or Markov random field, it's a NAND Markov random field. And what a NAND Markov random field is a graph with vertices and edges and weights, but all the edges are not potential functions, they're all NAND functions. So they basically say either one node is on or the other, but not both at the same time. And the way we do this conversion is we go through each clique in the graphical model on the left, and we say, let's create for every clique a group of nodes for each configuration of the clique and make them all pairwise adjacent. So for each clique, we've got 2 cliques, we create this group of nodes, all pairwise adjacent, and then we add extra edges between these pairs of nodes on the right-hand side if there's inconsistencies. And then we set the weight of these nodes as the weight of the clique at that configuration minus the min across all configurations. So this is a very simple algorithm to generate this Markov random field, this NAND Markov random field. And interestingly, now that we've built this alternative representation, we have a nice theorem that says if you solve the maximum weight stable set problem on the right-hand side, then you find the map estimate you wanted originally. Okay, so we've proven this. And the way to see this is basically map is trying to select for each clique a valid configuration and make sure they're all globally consistent with each other. So we maximize the total weight, and that's exactly what's happening now with this NAND Markov random field we've just constructed. Okay, it's basically the size of this graph is the number of scalars in all the different clique potential functions we have. We have one node for each scalar entry of the potential functions. Okay, so here's an example. We've got 2 cliques clique AB and clique BC, and these are the weights on them. These are the tables we would have. And then in blue are the original psi values and the potentials, and we subtract the min across everyone, and we get the blue weights for the Markov-Random field. And then we solve that problem as a maximum weight stable set. Okay, so let's just take a tree and convert the tree into a NAND Markov-Random field. Here's the example we're trying to reproduce. And it turns out for this little tree, we get this Markov-Random field, not NAND Markov-Random field. And then we just run this maximal stable set problem on that. So it turns out for trees, the NMRF we just obtained like this is a perfect graph, and this proves that it results from Perl from the 80s, okay? And here's the proof, but basically it uses these other lemmas we talked about. We derive the proof for stars, and then we paste stars onto each other to make trees, and that's a pasting of perfect graphs, so that's how we prove that the graph that we obtain through this compilation is perfect, and we can solve things efficiently. We also showed that it's possible in a maximum weight stable set to prune away any nodes with zero weight, solve the maximum weight stable set on the remaining graph, and then greedily add the nodes with zero weight back into the graph. Okay, because zero weight nodes aren't hard to optimize over. And then in addition, what we've shown is you can explore reparameterizations of your clique functions, and as long as your reparameterization from your original clique functions psi to psi primes maintains this equality, which means it doesn't change the probability distribution, you can use it. And so what we can do is we can get more zeros in our potential functions using these types of reparameterizations. We won't change our problem, but we'll get a simpler Markov-Random field at the end. And so we can actually explore a larger class by trying to also rewrite our potential functions so they've got lots of zeros in them. Okay, and so what we'll be doing is reparameterizing the potential functions a little bit, and we have different types of reparameterizations. One of them is called a singleton transformation, and we basically change the functions to simplify higher order potential functions, but by changing the smaller potential functions. And so this is very useful for pruning away a lot of nodes in our NMRF by mapping them to zeros and getting a lot of zeros. So here's a quick example. Upstairs we have two potential functions, actually three potential functions, psi1, psi12, and psi2. We have we have modified versions. These don't change the probability distribution, but what we've done is shifted weights around across these potential functions to create lots of zeros in the middle one. And so then instead of having a NAND Markov-Random field upstairs with 8 nodes, downstairs we're going to have a Markov-Random field with just 5 nodes. So it makes the problem simpler. And so by using this technique, we can also prove that for matching problems, the one that we had before, we can also convert those into a perfect NAND Markov-Random field, and that's why they admit efficient inference. So this proof just pops out without all the extra work we did with unwrapping the tree and so on. So we convert this thing to there, and we have a perfect graph we can solve efficiently. Also, if the Markov-Random field has all associative potential functions, so potential functions that like when both nodes are the same value, that also forms a perfect NAND Markov-Random field. And so that also is efficient to solve. It's shown on the right-hand side. And so we have a more general theorem which says whenever you have two Markov-Random fields, if they both map to perfect graphs, then we can combine them through this technique, and then the output graph is also going to be perfect. So we can grow two graphical models by combining them, and as long as we combine them on only one random variable, the resulting graph is, that you obtain when you compile them is perfect. And so this is useful. It helps prove our tree results, but it also shows that we can look at graphs by decomposing them into blocks and then applying this theorem. And so a block is a maximal two-connected subgraph. And we say graph is connected if there's a path connecting any two vertices, a graphical model is connected, and a cut vertex of a connected graph is a vertex that when you delete it, disconnects the graph. And a graph is two-connected or biconnected if there is no cut vertex, And a block is a maximal connected subgraph with no cut vertex. Okay, and so let's skip that. So here I'm showing a graphical model that's been built up by several blocks. And there you can see there's the red graphical model, there's the green graphical model, and there's a blue one, a pink one, and so on. We've pasted them all up. And this is a block decomposition of a graphical model. And so what we can do is we can use this block decomposition to prove some results on now Markov random fields where it's not just associative, but you have attractive and repulsive edges. And we'll show in dashed lines repulsive edges. So these are called antiferromagnetic, and in solid lines, attractive edges or ferromagnetic edges. And what we can do is we can decompose these types of signed graphs and only consider two connected blocks. And using the strong perfect graph theorem, we can say, will we get odd holes or odd anti-holes given this input graph if it has a certain pattern of associative and anti-associative edges. And so it turns out we don't have to worry about getting anti-holes of size 7 or larger for these types of models if they're binary mixed associative and anti-associative. But we could get holes of size 5. And it turns out these holes of size 5 in our NMRF conversion will arise if the original model has frustrated cycles. So a frustrated cycle means when I walk around in a cycle, I can get an odd number of repulsive edges. So over here I've got one repulsive edge in this cycle, one red edge, that's an odd number, that's a frustrated cycle. This cycle over here has two repulsive edges, that's not frustrated. Okay, so a frustrated cycle has an odd number of repulsive edges. And so we can now decompose the types of models that we can deal with and avoid getting a non-perfect graph. If there is no frustrated cycle in the model, then we have what we call a BR structure when we compile it into using our NAND Markov random field compilation. If we have a frustrated cycle with more than 3 edges, we will always get an odd hole and we won't have a perfect graph. Okay, so that's sad news. We can't handle big frustrated cycles. But it turns out if the frustrated cycle contains at least exactly 3 edges and only 1 repulsive edge or only 3 repulsive edges, then we can actually get these UN structures or TMN structures, which are perfect graphs when they compile. And so that's actually safe. We can have some frustrations in these graphical models as long as they're short frustrated cycles, but not long ones. We can still do inference and map estimation efficiently. And so as long as your binary pairwise Markov random field maps to compiles to an NMRF where all of its blocks are of the form BR, TMN, or UN, and I'll show pictures of these, then the map problem is going to be efficient. Okay, and so here's what a BR structure looks like. This is a graphical model without a frustrated cycle. And another way to view it is you can flip some nodes and make it fully attractive. And here are the TMN and UN structures. And this is these kind of graphs with any number of nodes as long as the left-hand side is all repulsive, the right-hand side is all attractive. And then downstairs are the UN structures. And here you've got every path from S to T has to have one repulsive, one attractive in it. So you can create these arbitrary large types of blocks. And you still will not have any holes, and the problem is going to be efficient. And so you can see here we've got cycles with 3 frustrated edges, or 3 repulsive edges. And over here we've got cycles with 1 repulsive edge. So these are frustrated cycles, but they're short. We're allowed to put those in. So what we can basically do is paste a graphical model from these different 3 types of blocks, and it's going to have some frustrated cycles, but they're going to be short. And then it still compiles into a perfect graph. We can solve the map problem efficiently. Okay, so here's an example. I pasted a bunch of these together. So to summarize, we showed how to reduce the NP-hard inference problem of either map estimation or actually marginal estimation, which I won't have time to cover today, by converting the graphical model into a weighted graph called a NAND Markov-Random field. And if that reduction produces a perfect graph, we know we can do inference efficiently. And so things aren't always NP-hard for inference with these graphical models. And so we've gone through a list of some known results. For example, acyclic models and trees, they form perfect graphs. Bipartite matching models will form perfect graphs. Associative models will form perfect graphs. And then we've also recently shown that now models without frustrated cycles form perfect graphs. Or we can have slightly frustrated models as long as the cycles of frustration are short and you only have, one or two repulsive edges in your frustrated cycles. You'll form a perfect graph and you'll be able to solve the map problem efficiently. And then in yellow, I'm skipping this result. You can also do the same type of conversion for the marginal inference problem. We have a paper about this at AI Stats. I won't talk about it too much, but you basically end up, again, a slightly larger NAND Markov-Random field, enumerating all the possibilities for your marginals, and then if it's perfect, you can also solve things efficiently. So here are some papers. I'll stop here and say thank you and take questions. Oh, so that's a good point. But in general, this is also hard even to get the approximate map. So if you really say, I want the solution that's within epsilon of the best one, that could also be very hard. Of course, if there are many solutions within epsilon like you're describing, because you've set up your model so that there's many good answers, then things could be easy. But we haven't looked into the approximate map estimation problems, which I think you're kind of alluding to. Again, you might not want to solve these things exactly, but even characterizing when you're epsilon away, takes a lot of careful work. That's a good point.
There's been kind of a lot of work done by listed and then Amir Benbow and speaking of this much more statistical physics problem and seeing how far from a tree and then looking at concentration type phenomena. Now, just wondering, it's a very different tack on the problem. Is there any overlap with the insights from the two, or
we'd love to find some overlap with those techniques. One of the things about these combinatorics results is, they're very new and very different in flavor. So, and most of these results are, they're not, with high probability type results. It's either, part of a family or not part of that family. But there are some connections now. So, there are these, like Zemeretti has some results that are, more probabilistic flavored combinatorial results. But yeah, we haven't found any connections. I'm aware of that work, and there's lots of other techniques you can use to argue for when map is efficient. This is kind of a very different tool set, I would say.